Okay, this is Brian Washburn. I like to do a problem, a central force problem. And so let's take a look at my force. So basically my force is a central force, has a term that depends on 1 over r squared, and also has another term that depends on 1 over r cubed. And so what I want to do with this problem is see if there's any stable orbits, and then I'm actually going to solve for the trajectory of the orbits. Okay. Now you may say, well, this is kind of well, where in the world would I get a potential that ever looks like this? Well, this is actually interesting. So notice that the first term here is 1 over r squared, so that's universal law of gravity. And then this is the next higher order term. And so if you look at these orbits here, it may get, for example, say Newton's universal law of gravity is wrong. All right, say it's wrong, and say there's higher order effects that affect it. By looking at this problem, and if you compare lambda to gamma, this is another higher order term. And so if you look at if the behavior of this actually matches nature, that tells me that Newton's universal law of gravity is incorrect. In fact, Newton predicted this himself. What Newton basically said was that if the universal law of gravity is not correct, then you would expect that the ellipses that the planets make, the axis would precess in time. And if you can actually measure this precession, then it shows that his law is incorrect. All right, Newton predicted that. Now, in fact, the ellipses do precess, and they precess because of relativity. So Newton's laws aren't exactly correct because of the Einstein's theory of relativity. So this is a good reason why to look at this problem. We'll talk a little bit more than class. So how we're going to solve this type of problem? Well, what we're going to do is we're going to write down a potential energy, then we're going to write an effective potential, and we're going to plot that effective potential and look under what conditions I'm going to get stable orbits from the plot. Then what I'm going to do is I'm going to use this force and solve for the trajectories. So let's just write down the potential. We can easily calculate potential just by taking looking at the integral. Remember the potential energy is equal to minus the work done by the force. Okay, we've done this enough, so we can say we have 1 over r minus 1 over r, and then I'm going to get minus lambda. Lambda. I have 2r squared here. Okay, you can take that derivative and get the force there, or minus that derivative to get the force. So now I'm going to write an effective force. In my effective force, remember I have to add that so-called centrifugal term to it. And so I'm going to get minus that. I'm going to get, so it's the same force, same potential I had before, but then I have to add this centrifugal term here. Okay. Now notice that the centrifugal term also has, that should be a square, not a cube. The potential square of the force is cubed. So notice that these two, the added term here has the same dependence as that. So now I can write down, I can just simplify things. So my effective force looks like something due to gravity. And then here I'm going to get 1/2. I'm just going to collect those terms here. Lambda L squared over mu, then 1 over r squared. Okay, so by a proper choice of lambda and L and mu, I can actually shut off that so-called centrifugal term. All right. So what I want to do is I want to plot the effective potential, but I have to plot it for different conditions. Okay. So there's 3 conditions I have to plot this for, and it depends on the values of lambda with respect to L squared over mu. So if I plot, let's look at case 1. Okay, my first case is that lambda is less than L squared over mu. Okay, that makes this thing here a negative number. That makes the whole thing a positive number. So U effective looks like that, and then I'm going to put here plus 1/2. I'm going to use absolute value, so that gives me again a positive number. Okay, that's what I have there. So I want to sketch that effective potential. Notice that one term is positive, one term is negative. So then the negative term is the so-called universal gravitational term, 1 over r, so that does something like this. And then the other term is positive 1 over r squared, so that dies a little faster. That. Okay, and then the net potential is going to look something like this. So this, the cool thing about that, something like that, that's a sketch. Now that looks exactly like the same effective potential we had for the Kepler problem, and in fact it is. So from this I expect to get bound orbits. In fact, I expect to get bound orbits that look like circles and ellipses, and for negative energies. For positive energies, I expect things to look like parabolas and hyperbolas, and you can easily show that, and we'll do that in a minute. Because that's for that case there. Now we have 2 other cases. Let's go to the next slide for that. The next case is what I'm going to do is I'm going to set lambda equal to that thing there. Now in that case what happens is the u effective, the 1 over r squared term goes away, and then I just get gamma minus gamma over r. Well, if I were to sketch that potential, that just looks like this. And there is no bound potential. Okay, so that is, if I have that case, and that again is case 2, I'm going to get no bound orbits. And finally, case 3, this is where delta is bigger than this guy here. I can write u effective as, so this is my gravitational term, and then I'm going to have minus 1/2, and then I'm going to put again absolute value, but you notice I have a minus sign there. U 1 over r squared. Yep. And that guy, we sketch that potential out. We have 1 over r squared, minus 1 over r squared, and then we have minus 1 over r. This is minus 1 over r, minus 1 over r squared. And so it's just going to do something like that. Sorry, it doesn't cross, of course. It goes to 0. Okay. Again, I'm not going to get any bound orbits. Okay, so now what I'm going to do is let's look at I want to look at the trajectory of bound orbits. Okay. And so let's look at the case where I have bound orbits. That's case 1. And what I want to do is I want to solve for the trajectories of those orbits. So let's do that. Next slide. Okay, so I rewrote my effective potential, but really what I want to do is I want to look at this force and stick that force back into that differential equation that we solved. And that differential equation, to get the trajectory, remember what I did was, just to remind you, I defined a variable u, okay, and I want u as a function of phi. Again, that's the trajectory of the thing. U is going to be defined as 1 over r of phi. I want to solve for not r as a function of time, but r as a function of phi. Okay. And then the differential equation I derived in class, where basically I showed that u, the second derivative of u respect to phi, that's u double prime, is equal to minus u of phi. Then I'm going to have here mu, that's the reduced math, L squared u squared of phi times the force respect to written in u. So that's my differential equation. So now what I want to do is let's rewrite my force here. So here I have the force. My force, not in function of r, is going to be equal to minus gamma u squared minus lambda u cubed. So I'm going to stick that into my differential equation I have there. I'm going to get u double prime is equal to u minus u. Okay. And then here I'm going to get plus, and I'm going to, so I'm going to get mu L squared u squared, and then I'm going to get here minus gamma u squared plus or minus delta u cubed. So the problem looks very similar to what we did for the Kepler problem, except we have this now u cubed term. It's going to be a linear term. All right. So it's, however, nothing really. Okay, let's go through a little bit. So then if I do this, if I multiply through here, I'm going to get, oh, by the way, there's a minus sign. So this, sorry, I made a mistake. That's a minus sign there. So minus minus, that gives me plus. So I'm going to get a constant mu gamma L squared. The u squares cancel out. And then I'm going to get another plus, except here I'm going to get mu lambda L squared times u. Now, the cool thing about this equation here, my functionality hasn't changed. When I did the Kepler problem, I had, on the right-hand side, I had a linear term in u and a constant term. Here, I still have that linear term, a constant term, and then I get another linear term. So in the end, I get the same form of the differential equation. So I expect to see something that looks similar in my solutions. Okay, so let's just go down and rewrite this equation in a little nicer form. So I get u double to prime is equal to, now I'm going to say I'm going to factor everything out in front of that u. All right, L squared mu minus 1 u, and then I get that constant term mu lambda L squared. Okay, so this is the same form of the differential equation, I just have different constants. So what I'm going to do is I'm going to try to get it in a similar form as what we had before with the Kepler problem. I'm going to define a variable eta, and eta I'm going to define as this. Now eta is going to be an important parameter because what's going to happen is when eta squared equals 1, okay, so how do I get this problem to look like the Kepler problem? I set lambda equal to 0. That makes eta squared equal to 1. Okay, so I'm going to define that. Again, basically what lambda represents the perturbation of the potential from Newton's universal law of gravity. That's really what lambda, that's physically what it means. All right, so let's do this. So in some respects, eta is also a measure of that. Okay, so that's cool. Now let me kind of type down a little bit. And so now I can write, I'm going to get a differential equation that looks like this. Sorry. Okay, u, that's squared. So this again looks very similar to what we had before. Okay, so that's my differential equation. And again, it looks like simple harmonic motion. Okay, so let's solve that differential equation on the next slide. Okay, so this is my differential equation here. So it kind of looks like simple harmonic motion with a constant. So how we're going to solve it, I want to get it, just rewrite it in the form of simple harmonic motion. I'm going to define a w, and I'm going to define w as eta squared u minus gamma mu L squared. Okay. If I take the second derivative of that, that's just going to give me eta squared u double dot. Okay. And that means from that equation, u double dot is, or u double prime is equal to w prime eta squared. So now I'm going to take this and put it back into that equation. If I do that, oh yeah, then just to make things more transparent, I'm going to use this equation to solve for u. U is going to be equal to w plus gamma mu L squared, then 1 over eta squared. Okay, so I'm going to take this u, put it in here. I'm going to take this u double prime, put it into there, and then I get rid of the u's. And if I do that, I get w double prime eta squared. And then here I get minus eta. That's from, sorry, I forget. Yeah, that's from that term. The minus eta squared is from that term there. So minus eta squared. Then times all this stuff that's u. Okay, and I get this bad boy here. It's a lot of monkeying around to make a simple equation. We'll get there. Okay. Now when I multiply through, the etas cancel out. This term here eventually is going to cancel out with that. And then by simplifying, you can easily see that I get this. So my differential equation is just that. Okay, so that is simple harmonic motion. A solution to that is W is a function of phi is going to be equal to, you got to be a little careful here, some constant A, and then have eta there plus another constant. That depends on my initial conditions. We can rewrite U. We want to rewrite U. So U is going to be equal to, just using that. Let's get, this is in general. We can always find some initial conditions where delta is equal to 0. We're going to get that. A cosine eta phi plus this constant here. There is, it's L squared. Sorry, L squared. Eta squared. Okay. And then what we can do at this point, we can rewrite this in a similar way. Instead of writing in terms of A, I want to write it in the same way we wrote the Kepler problem. So I'm going to say delta eta squared U is going to equal to, and this is the same way we did it for the Kepler problem. This kind of rearranging constants. 1 plus the eccentricity, but you got to be careful, we still have this eta term in here. Okay. Where the eccentricity, as we defined before, is just a L squared, just a constant. And it will depend on total energy of the system. Now at this point, what here I can do is, whoops, why did I do that? That is weird. So at this point here, what I'm going to do is set U equal to 1 over R. So I'm going to get here eta 1 over R, eta squared 1 over R is equal to this business here. Epsilon naught, yeah, that's not epsilon naught. These are not E&M problems. Okay, so, and then I can, again, instead of E, I can use another constant, the same constant. We define a constant C, where C is equal to L squared over mu delta. And so let me just write the final result. I'm going to get eta squared C over 1 over R is equal to 1 plus epsilon naught cosine eta. That's it. Okay, that's my answer. Now, what did we get for the Kepler problem? Well, we got for the Kepler problem was that we got the same result for the Kepler problem, except what I showed there. Let me write it below. I showed that C over R is equal to 1 plus epsilon cosine of phi. That's what we showed for the Kepler problem. And that makes sense based on, you know, for eta, remember if there's no cubic term, then eta squared will equal 1. And that's where we get the Kepler problem. So again, just as a reminder, what are we doing? I mean, what we're doing is we're saying we have a force. This force has a term here that looks like gravity, universal law of gravity, plus some perturbation, okay? And that perturbation happens to be a 1 over r cubed term. And so then what happens is we get something that looks like Kepler, except we have this eta term. Now, eta is going to be important because what happens is if eta is not a, say eta is of some non-rational factor of pi, then the orbit's not going to close upon itself. And so then what you'll see is you'll see an ellipse. Say I set For example, remember epsilon. Say I do a problem where I set c equals to 1 and epsilon equals to 0.5. That's an ellipse. But as it kind of comes around, so basically if in a Kepler problem, I'll have an ellipse like this. Okay. But in this problem here, what will happen is that if eta is not a rational, some factor of pi or something like that, it's going to come around and then miss, and then it's going to do this, and then miss the second time, and do that, and miss, and do that, and miss. That's kind of what's going to happen. Well, from looking at it, that's a precessing ellipse. And so if you go out into, look at a solar system and you see a precessing ellipse, if you live long enough to see such a thing, then you say, hey, Newton's laws don't work. Okay. In fact, people see this. People see this with Mercury, and what's causing that is special relativity. Okay. So what I can do is we can plot these trajectories, and I have code on Python. It's called Physics 522 Strange Orbits. And so what I do is I create. So what do I do? Okay, now I create values of phi, and I have 5,000 points, and I go from 0 to 30, 30 times 2 pi. So it goes through a circle 30 times. Okay. And the reason why if I do that is because the orbits are going to precess. Okay. And then what I do is I take c equal 1, epsilon equal to 0.5. That's an ellipse. And then I say eta. I pick some eta. Now in this case, I do make it a fraction of pi, so pi over 3. You can see even for this case, I get closed orbit. I do not get closed orbit. And then to find my eta. And this is what I get. So you can see, now again, I don't have enough pi rotations for it to completely, but you can see at one time the orientation of the ellipse is like this, at another time, so you get this precessing ellipse. I can make it complete. See if I make it 10. If I make it 10, then it doesn't precess as much. Okay, let's even make it, let's make it 3, and it should precess a few times. Yeah, so there you can see it's almost, you haven't even precessed once. That's n pi. Oh yeah, 3, that makes sense. So let's do 6. So you can see it precesses a few times. If I call this 60, it should precess all the way around. There's my nice spirograph there. Okay. Now let's do this. Let's set eta equal to 0. Okay, I've set eta equals 0, and then I'm not sure what's going on there. Oh, I know why. So, eta equal to 0. Sorry, it can't be 0. Eta has to equal to 1. Remember, eta depends on the difference, and so when lambda equals 1, then eta squared equals 1. So if I do that, then I get an ellipse again. Okay, so you can play around with that. So if I just do MP pi divided by 2, let's see what I get there. So I get these kind of precession going on. Let's do maybe something crazy. Yeah. Okay. So that's what's going on. That's kind of cool. Yeah. Let's just reduce this down to say 3 and see how it does it for a few of them. Yeah, so that's kind of cool. So you kind of get this funky shape. So it's kind of neat. Just by adding another term, you can create a test for a 1 over r squared gravitational potential. And we can easily solve for the trajectories using methods that we learned here. That's pretty powerful. That's the type of problems you can do, central force problems. We'll see you later. Bye-bye.